Imagine a bustling city with towering skyscrapers, busy roads, and people going about their daily lives. It's a picture of modern civilization, but there's a hidden cost. The very fabric of these structures, the concrete, is a silent giant in terms of greenhouse gas emissions, responsible for 8% of global total. Concrete is the second most used substance in the world after water. Its role as a building material is so woven into the fabric of our lives that it's almost invisible in plain sight. If you're sitting in a building right now, you are, in essence, cradled by concrete. But what makes concrete so indispensable and strong? The secret ingredient is cement. Cement's what binds everything together and gives concrete its strength, and it's also where most of the emissions come from. In 2021, more than 2.5 billion tonnes of CO2 were released from cement production. While cement in concrete can be recycled, the demand far outstrips the amount recycled each year, which means we have to produce a lot of fresh cement. There are things we can do to limit how much we use, but because developing countries are using increasing amounts of cement to build housing and infrastructure to improve living standards of their booming populations, we're going to need more and more each year for a while yet. That means we need to find a way of producing it without the emissions. And unfortunately, cement making is likely to be one of the most difficult sectors to decarbonize. But though it's difficult, it's by no means impossible. In this video, we're going to take a look at how traditional cement production works, where the CO2 comes from in that process, why it's so hard to get rid of, and how we can make cement without any CO2 emissions. I'm going to try and make the abstract concepts a bit more concrete. I'm Rosie, a mechanical engineer with a PhD and a couple of decades experience developing energy transition technologies. Welcome to Engineering with Rosie. Let's start by laying a foundation and clearing up the difference between cement and concrete. These terms are sometimes used interchangeably, but they're not the same thing. Concrete is a mixture of cement along with sand and gravel, which is used as a building material. When water is added to the mixture, it forms a fluid-like slurry that allows it to be poured in place where it will harden over several hours. Most concrete is poured with reinforcing materials like rebar to increase its strength. Cement is the most important ingredient of concrete, as well as other building materials like mortar for masonry. It's the part of these materials that makes them stick together, and it's almost never used on its own. There are different kinds of cements. By far the most commonly used today is Portland cement. Its main ingredient, making up to 95% of it, is a substance called clinker, and the other ingredients are gypsum and fine limestone. The clinker acts as the binder in cement, and production of clinker is what's responsible for most CO2 emissions from cement. So quick recap, clinker is the main ingredient of the most commonly used type of cement. Cement, in turn, is the main ingredient of building materials like concrete. I mentioned that emissions from cement are going to be hard to get rid of. In order to explain why, I'm going to quickly take you through how it's produced. First, limestone, calcium carbonate rock, is crushed and ground to produce a powder called raw meal, which also contains supplementary materials like silica, alumina, and iron that are needed later in the process. Next, the raw meal is heated in a kiln in one or several stages. At around 900 degrees Celsius, the calcium carbonate in the limestone begins to decompose in a process known as calcination. This composition releases carbon dioxide and leaves behind calcium oxide. The CO2 is emitted into the atmosphere, and this part alone is responsible for about 2/3 of the emissions from cement production. The CO2 that's emitted here is a non-negotiable part of that reaction because limestone is 44% CO2 by weight, which is trapped in the rock, and it's released when making lime. If you want to turn limestone into lime, you simply cannot avoid releasing CO2. As the temperature increases to around 1450 degrees, calcination continues, and the calcium oxide reacts with the silica, alumina, and iron to form compounds known as clinker minerals. The really hot temperatures needed for this process usually come from burning fossil fuels, resulting in more CO2 emissions. Burning fossil fuels isn't the only way to heat things, but the high temperatures needed rule out some of the easier clean heat alternatives like heat pumps. And it's these problems together that makes eliminating cement emissions so difficult. But there's nothing that engineers like more than a problem, and engineers and other experts around the world have developed a number of methods to reduce or remove cement emissions, so let's go through those now. To start, we can reduce emissions from cement just by using less of it. We use far more cement than we need right now. A lot of building standards, for instance, require a certain amount of cement when what they're really trying to accomplish is a minimum amount of strength. This results in using a lot more cement than necessary a lot of the time. Moving from material standards to performance standards would be a good way to deal with this. Another thing that would help reduce cement usage would be increasing the recycling rate of concrete. Estimates for current recycling rates vary a lot, from as low as 20% to as high as 80%. So there's at least a little bit more we can do, and maybe a lot more. The components of concrete can be partially recovered and reused when an old building is demolished. As long as a clean source of energy is used for the heat needed in the recycling process, emissions are negligible compared to virgin cement production. There are also several technological solutions for reducing cement usage. A company called Carbon Cure has developed a technique that involves injecting CO2 into concrete. They claim that this actually increases its strength, and because it's stronger, around 4 to 6% less cement content is needed. And as an added bonus, the injected CO2 stays there permanently, with about 13 kilograms of CO2 per cubic metre of concrete sequestered. The use of geopolymers as a cement substitute is another option. Geopolymers are a type of cementitious material that can be made from a variety of materials, including fly ash, slag, and recycled concrete. Because they don't use limestone and they don't need high temperature processes, their manufacture can be up to 70% lower emissions than traditional cement. Aside from replacing cement with lower emissions alternatives, another possibility is to lower the clinker content of cement. Because clinker is the emissions-intensive part of the process, a lower clinker content means lower emissions. The global average clinker content is about 65%, and the average in China is about 57%, with the difference coming from what's known as supplementary cementitious materials, mainly industrial byproducts like fly ash, blast furnace slag, and silica fume. It's usually cheaper to produce less clinker, so the use of supplementary cementitious materials is already widespread in the cement industry. One problem with this is that the road to net zero in other industries is likely to limit our access to many of those materials. Fly ash is a byproduct of coal, and blast furnace slag is a byproduct of blast furnaces in steelmaking. As coal usage goes down and the steel industry moves away from blast furnaces, availability of those materials is going to dwindle, meaning that there are going to be some limitations on this method going forward. But there are other materials that could be used to replace these substances, which we're not making much use of right now. A company called Terra CO2 has developed a technique for using silicate-based igneous rocks. Calcined clay is another possible alternative, and a Danish company called FutureCem has developed a method of combining calcined clay and limestone to replace 40% of the clinker in cement. Now, using less cement and less clinker in that cement will help to reduce the amount of CO2 released from turning limestone into lime. But what if we were able to avoid that process altogether? Limestone is the most common type of rock used in cement manufacturing, but it's not the only one that can be used. A US startup called Brimstone has developed a method that they claim produces no process emissions, creating cement from calcium silicate rock. The final product is chemically identical to Portland cement, but because there's no carbon in the source mineral, there's no CO2 produced. They have reportedly produced a small amount of zero-emission Portland cement from this method for the first time in 2022. And there's another US startup called Sublime who are working on low-temperature processes to either start from limestone and capture the CO2 from that reaction, or to take calcium out of different minerals and so avoid producing any CO2 at all. So those are both very interesting, especially because it should be possible to combine one of those processes with CO2 injection like Carbon Cure is doing, in which case you would end up with carbon negative cement. But given that in both cases it's still very young technology, it's a bit too early to say for sure if this production method will be able to scale up to the level required by 2050. If we can't get rid of all the emissions, we could still get to zero emissions by either preventing the CO2 released from escaping or by trapping an equivalent amount of CO2 from somewhere else. There are a few technologies that can use cement to permanently store carbon dioxide that's been removed from the atmosphere. We already mentioned Carbon Cure, who injects CO2 into concrete. And then other options include mineral carbonation, which I covered in this video when I visited MCI International, and magnesium-based cements, which can absorb carbon dioxide over time, allowing us to use them as a carbon sink. And finally, there's carbon capture and storage, CCS. Put simply, carbon capture works by grabbing and concentrating CO2 emissions from point sources like a coal power plant or a cement factory, and then storing it underground so it never makes it into the atmosphere. When it comes to something like a coal power plant, this doesn't really make any sense because it's far cheaper and more reliable to simply get rid of the coal power plant and replace them with renewable electricity generation and storage. When it comes to cement though, carbon capture may be our only choice. If we aren't able to scale cement production from non-carbonate sources, carbon capture may be the only way to deal with process emissions from cement, making it the industry where carbon capture is likely to be the most essential to net zero transition. Carbon capture is already in use in a number of cement plants worldwide. Collectively, these plants captured about 100,000 tons of CO2 in 2021, which may sound like a lot until you remember that cement is responsible for 2.5 billion tons of CO2 each year. A lot of scale-up would be needed to even make a dent in global emissions from cement. And so far, scaling up CCS is something that has stumbled along, making very little progress for decades now. The scale of carbon capture required reinforces why using less clinker in our cement, as well as using less cement overall, is going to be important. Getting rid of cement emissions is just really hard. So those are all technologies with the potential to remove process emissions, but that still leaves emissions from heat. On that front, there are a few options available. Finland-based VTT has launched a project to develop electric kilns for cement making. In early 2022, they were able to produce clinker without fossil fuels for the first time, with plans to scale up the project over time. Two other projects, Heliogen in the US and Solpart in France, are attempting to get the energy for the kiln directly from concentrated solar sunlight. Both have reported achieving temperatures exceeding 1,000 degrees Celsius so far, so getting close. So those are the technologies available to get rid of emissions from cement. Add a few of them together and zero emission cement is within reach. Though I really need to add the caveat that we are certainly not close to a time when those technologies come at the same price as traditional cement. So this is one instance where the technology on its own is not going to be enough to eliminate emissions. It'll need to be combined with policies to promote fast adaptation. Thanks to the Engineering with Rosie Patreon team who support all the research needed to make these videos. If you'd like to join us and get access to the Patreon-only Discord server and help shape future videos, then you can do it at this link. Thanks for watching, and I'll see you in the next video.